All right, so today is the second lecture in our gas laws. Last time I was kind of hinting at you about a new character on our wall, the molecular weight kitty cat. It's molecular weight because, what does the cat say? Now, oh, we have a cheetah in here today, so how appropriate. So normally we say molar mass, but for the sake of the character, we say molar weight. This particular equation I love. It's a shortcut to a couple gas law questions where I'm going to kind of tell you the long way to do these, but I really only think you should use the molecular weight kitty cat. And I was going to say something. The formula is molar weight of a gas is equal to, and here's what I want to know. How many of y'all have a cat? Okay, there's a lot of you. Cats go in their litter box, right? They do their stuff, and then what do? They bury their stuff, right? So what they're actually doing is putting their dirt over their pee. So if you look up there, there's the molecular weight kitty cat. When do you use this formula? There's two cases, and they're very common cases. They're used to, number one, find density of gases at many conditions. And then we can also obviously find molar mass of a gas. Now this equation comes about through deriving from putting a couple things together. And I'm going to tell you how to do these the long way, but stick to the short way for actual problem solving. So the problem here says calculate the density of oxygen gas at STP. Let's talk about the units on all these, so I want you to see that the units actually do work out. Molar mass has what units? It's not a trick question. I know you all know this. Grams per mole, right. Okay. Density for liquids, we usually did grams per mil, but in gases, we actually do density as grams per liter. Can anyone tell me why? Right. It's really, really tough to weigh or get a significant enough weight for a mil of a gas because they're so light. We want to use a larger sample. Okay, so we usually measure in grams per liter. The R is that universal gas constant, 0.0821 latam mole. What do you think the K is in? The T is in? Kelvin. And then guess the pressure. ATM. Correct. So looking at this, does this stuff cancel? Well, liters cancel with the density liters. Atmospheres cancels here. Kelvin cancels. Grams over moles. Isn't that fun? Okay, so the units do work out really well. So let's plug in our information. If we're looking for the density of an oxygen gas, the molar mass is what of oxygen gas? 32, it's diatomic, 32 grams per mole is equal to, density is what we're solving for. What's R? 0.0821 latam mole. Temperature? STP, so 273, and that's Kelvin. All of that divided by STP, pressure, or ATM. So let's go ahead and solve. So the answer is 1.43 grams per liter. All right, let's do one more of these, but instead of actually finding density, we are going to solve for molar mass, once I can reach that. A compound has the empirical formula of CHCl. That's our empirical formula. It says a 256 mil flask at 373 Kelvin and 750 torr contains 0.80 grams. We need to find the molecular formula. All right, we know the empirical formula, and we can figure out the empirical formula's mass. What would be one way to find the molecular formula? Find the molar mass. Once we find the molar mass, we can take that and then figure out how many times greater the molecular formula is than the empirical formula, right? And then go from there. So our molar mass, this is a gas, so we use molar weight kitty cat, dirt over P. So we are solving for molar mass. I don't know what the molar mass is equal to. Now, density is grams per liter. Do I have that information? Yep. 0.80 grams. And what's my liters? 0.256. D, that's D, R, 0.0821 lattimolc. DRT, what's my Kelvin temperature? 373. And my pressure, we got to convert to atmospheres. So again, as an AP reader, I want to see the conversion. So as long as I show that, I can do that, and then that'll be in atmospheres. So molecular mass of this turns out to be 96.97 grams per mole. So that's the weight of the molar, or the molecular formula, okay? Does anyone know what the weight of the empirical formula is? 48.46. This one weighs 96 something. What's the relationship there? Double. This is double. So what is my molecular formula? C what? C2, H2. Good. Cl2. And therefore, I have my molecular formula. Okay, so those are the shortcut ways. For those of you who want to know the long cut way, come talk to me. The long cut, is there such a thing? But again, I'm thinking this is the best way to handle it. If you're having issues with this formula, come talk to me and we'll do it a little differently. Okay, now, love this. I'm going to do a little stoichiometry with gases. I'm going to call it gassy stoich. It's gassy, 2 S's. Gassy stoich. It doesn't look right. You often write gassy, so I'm probably not a good judge of that. We are ultimately looking for the volume of H2. So what volume of H2 is formed at, and these are the current conditions, 0.98 ATM and 450 degrees Celsius. I need to move this in case there's something I'm missing. When we're starting with 98.3 grams of the water. So, you see why I'm calling this stoichiometry? We're starting here, and we have to mole bridge to there. But we're looking for a volume. Can anyone tell me why we aren't allowed to use 22.4 liters per mole after I do my stoichiometry? Very good, not at standard conditions. So what am I going to do? Where do I stop? What do I find first? Find number of moles of what? Of H2 with stoich, and then what do I do? Then what? No, that's a little too hard. So now that we have found, once we find number of moles using stoichiometry, we're going to use an equation to then convert those moles to volume. What is that equation? Very nice. Okay, so PV equals nRT. We'll take those moles, plug them in along with all the conditions from the top, and solve for our volume. Okay, so let's start the stoichiometry. Start with my given of 98.3 grams of H2O. What do I convert to? Moles of H2O. So for every 1 mole of H2O, I have 18.02 grams. It's the molar mass of it. Now I got a mole bridge. What's my mole ratio? 4 to 4. Good. 4 moles of H2 on top, 4 moles of water on the bottom. Now, if this were at actual standard conditions and I wanted volume, I would continue the stoichiometry here and then do 22.4 liters for every 1 mole. But we're not at standard conditions, so we have to stop. So go ahead and give me the moles of my H2, the 3 sig figs. 5.46 moles of H2. All right, so now we'll plug into PervNert. Pressure they gave us as 0.98 atm, which is good news because we want it in atm. We are looking for volume. The number of moles we just calculated was 5.46. R is always 0.0821 in gas laws at least. Lattimole. And then the temperature right here again, we got a problem. We're in Celsius. 450 degrees Celsius plus 273 will give us our Kelvin temperature. I'm okay with you doing the conversion like that. Again, if you don't like this and that bothers you, do the conversion somewhere near it so those grading the AP can see it and know that that's Kelvin temperature. What you can also do is actually do the addition. What does that come out to be when I add those? 723? All right, so you could do that too if you want. All right. What is our volume? 3 sig figs. 331? And the unit? What? Liters. Good. That's a lot. That's a whole heck of a lot. Okay, so the kinetic molecular theory is something that's going to be useful to you this year specifically because on the AP exam you guys are going to have to answer a lot of free response questions. Part of those free response questions have short essay parts, short answer parts where you have to use words to describe things that we have just taken for granted. Like when you increase temperature, pressure increases. You got to explain it. So a lot of times you don't have an arsenal of vocabulary or ideas to use to approach that. The kinetic molecular theory is what you're going to be using. I do not want you to sit here and memorize the first postulate of the kinetic molecular. No. We're going to read through these. They're kind of duh. That makes sense. You know all these. But this is what you're going to use and kind of refer to when you're answering your questions. After we go through this, tonight I want you to do your free response problem number 1. Those are due the day before the test, so we can all go over them in class. But this is a good time to work on that because you're going to be using this kind of as an explanation. So, number 1, the kinetic molecular theory says gases consist of tiny submicroscopic molecules which are in continuous random motion. We're going to learn later that there's a difference between what we call an ideal gas and a non-ideal gas. Ideal gases, the gases we use PV equals nRT with, all those perfect gases are very, very small, and they technically almost have no volume. They're kind of just points in space. So gas molecules are supposed to be ideally super, super, duper, duper small. Okay? And we're going to delve into this more tomorrow when we talk about the van der Waals equation. The second says the distance between molecules is large compared with the size of the molecules in cells. The volume occupied by a gas consists mostly of empty space. So what, who cares? Well, this is why we can change the volume of gases so easily. Can you easily change the volume of a solid? No, those molecules are already pretty packed. So changes in pressure don't affect volumes of solids and liquids much at all. However, gases, because of the distance between the molecules, pressure effects have a very, very huge effect on them. Pressure changes have a huge effect on them. Another thing that ideal gases have, ideally, they have no attraction to each other. If molecules were attracted to each other, what would they be? Would they be really gaseous? No, they'd be closer together, right? They'd be more apt to be liquids and solids. So in order to be a gas, these molecules really can't be attracted to each other. So reach into your last year brain and think about intermolecular forces. When something has an intermolecular force that's not very attractive to each other, what were those called, those particular forces? Not polar. Polar was attracted, so nonpolar. So these are more of your nonpolar molecules or your small molecules as well. What does small have to do with intermolecular forces? Small molecules. And we're going to talk again more about this tomorrow. But if you have a molecule that's huge, say we've got a nucleus and we've got, I'm putting a ton. It's huge and it's got a bunch of electrons. Okay. Even though it's nonpolar, if there's just like a Br2 or something like that, if it's got a ton of electrons, when it runs into other molecules, all the electrons can kind of shift to one side. And shifting to one side, we have a partial negative and a partial positive polarity created. So if we have a bunch of electrons, we tend to have more attractive forces than if we just had, hydrogen. Okay? So ideally, gas molecules have no attractive forces, so we want them to either be nonpolar or small to be the most ideal. And we'll talk about ideal versus non-ideal tomorrow. Number 4, gas molecules move in straight lines in all directions, colliding frequently with one another and with the walls of the container. What is colliding frequently with one another and the walls of the container called? Pressure. So that's kind of the whole point. That's where we get pressure. If gas molecules didn't move around like that, we wouldn't have pressure. What's also important is the fact that these are elastic collisions and no energy is lost. If every time molecules hit each other and energy were lost, what would happen to pressure as time went by? Decrease. And that doesn't happen. Pressure remains pretty constant unless you change temperature or volume or something like that, right? So, due to the fact that the elisions are elastic, pressure pretty much remains constant. Okay? And then the last one is kind of important, and again, we're going to derive some of this stuff in the next couple days. The average kinetic energy for molecules is the same. This is so important for all gases. This is not like physics, okay? In physics, what was the formula for kinetic energy? 1/2 mv squared, right? That's the kinetic energy of one little thing, one ball or one atom or one whatever. We look at the average energy between moles and moles of molecules. We're going to learn this equation tomorrow, but kinetic energy, the average kinetic energy, is equal to 3/2 RT. R is that gas constant we know and love. We're looking at changes in temperature. So what I want you to get out of what I'm about to say, the only thing that changes the average kinetic energy of gas is changing temperature. Average kinetic energy is temperature dependent. That's crucial. And this will apply to AP problems that we're going to work in the next couple days. So those are kind of common sense, right? So now this is what I want you to use to answer tonight's question. Tonight's question was something about, I think it says pressure increases, temperature increases, and the question said, using the kinetic molecular theory, explain this. And so, which ones relate to temperature and pressure? Which of those? 6 is gonna talk about, so if we increase the temperature, what happens first? No, not directly. We're increasing the kinetic energy, which then affects what? Our collisions and what the collisions with the wall of the container. So we can pull in 5 and mostly 4 in that explanation. Now don't say number 5, number 4, but you have to put it into a nice little compact. And don't write a ton of words. I'm talking 3 or 4 sentences will answer this. But you need to sound intelligent, and you just can't say cuz. I mean, you have to, if you're saying temperature increases, kinetic energy increases when you increase temperature, I kind of want you to use that formula and show that as proof. But play with that in the next few minutes. It shouldn't take you but 3 or 4 minutes to come up with an answer, and that'll be it for the day.